Good evening. My name is Rishi Ghia and I am SAP number 60001180048 from final year electronics from DJ Sanghvi College of Engineering. My email ID is listed above and my project guide for this project will be Professor Darshana Sankhe ma'am. My topic is navigation and docking of a UAV onto an aerostat, or the actual name of the project will be modeling and simulation of the docking of a UAV onto a moving platform. Now, my project is going to be consisting of many parts. So let's go over a short introduction in order to understand what is it that I have accomplished and will be talking about in general. So we could just take a look at this diagram right here. And here we can see that there is something that we call an aerostat. Now, an aerostat is in general just an airship that is going to be filled of a lighter than air gas, such as hydrogen or helium. Helium because it is going to be less explosive, less volatile, noble gas. And on top of that, we will be having a certain flat base, which we shall call the platform, on top of which we'll be having one or more UAVs. As shown in this diagram, we can have two UAVs. Now the UAVs have the ability to take off and land from and onto this platform. And while they are on this platform, the goal is for them to be able to swap their batteries out so that when they run out of battery, they're able to quickly turn around and fly back up again. And finally, the aerostat shall be connected to the ground using a conducting tether. This tether has to be conducting as it has to be able to supply power all the way up to the top. And then there will be a relocatable ground station, which should ideally be able to take the aerostat and rather the entire system and move it to a different point rather easily without any more setup costs or more setup time. But why is it that we even need a system like this? This may seem like an overly complicated solution to just have UAVs roam about here and there, but there are a few very good reasons for that. That is because in today's world, we have an increasing need for UAVs, and that is because you could have a million applications for them. You could have them in the commercial sector, where you could have companies like Amazon perform delivery of products. You could have it in the agriculture sector, where you could autonomously have UAVs fill in fertilizers and pesticides for the crops, and in fact even perform seeding of the ground. And you could also have military applications where you could have surveillance and applications like that. The applications are immense in simple terms. But the problem with UAVs in today's world is that they have a rather short range and they require expert flyers. And both of these problems are ones that we intend to solve with this project. So with this project, what we intend to do is that instead of having UAVs be something that are piloted around by expert pilots, which costs time, money, and effort, we shall have the entire flight path be automated and pre-programmed. And not just that, the hard part of why the pilot is required in the first place is the landing, which is what we shall be aiming to make autonomous. And secondly, in order to solve the problem for the range, we shall have the UAVs come on and autonomously land onto this aerostat. The battery shall be swapped with a fully charged battery, and then the UAV can take off. And while the UAV is flying, that uncharged battery or that discharged battery will now be able to be charged right on top of the aerostat. But now you may ask, why do we need an aerostat in the first place? Can't we just do this on the ground? Yes, we can. But here the entire point is efficiency and the ability to be able to deploy a UAV very quickly. By having an aerostat at an altitude of maybe 100 or 150 meters, what we're doing is we're saving a lot of the energy it might take for the UAV to be able to go from an altitude of 0 to that altitude of 100 meters. And that VTOL part, vertical takeoff and landing part of the UAV's flight path, is the one which is the most inefficient. And using an aerostat, we get to solve that. So now that you've understood what the project is about, we can move on to certain parts of the project. So the way we shall proceed is, first we shall understand what the landing constraints are, such as we'll have a moving base. We require to stabilize the UAV once it lands and hold it in place, that is the arresting. The landing area is going to be very restricted because since we're on an aerostat, we'll have a very small base or a very small landing area. Attitude specific landing, that is, we cannot just land in any orientation. We need to land in a very specific orientation in order for the battery to be removable and chargeable. And finally, we want this to be a universally applicable and scaling system. That is, this system should not just work for UAVs of a particular size, that is the ones that we've tested it for, but it should be able to scale, other manufacturers should be able to scale it up for their respective applications. Then we have the selection of the unmanned aerial vehicle. We have four different types here. That is the multi-rotor UAV, the fixed-wing UAV, the single-rotor helicopter, and the fixed-wing hybrid VTOL UAV. A multi-rotor UAV is a standard drone. It's the one that you will see everywhere, here and there. You will see it on YouTube, etc. A fixed-wing UAV is basically something like a commercial aircraft, just without any pilots. It flies on the basis of its wings. Then we have the single rotor helicopter, which is the standard helicopter. And then we have the fixed wing hybrid VTOL UAV. It sounds complicated, but it's really simple. It's basically a combination of the multi-rotor UAV and the fixed wing UAV. Now, this is the one that we have selected for this project, and that is because the multi-rotor part of the UAV allows for the UAV to be able to take off and land very easily. Basically in a vertical takeoff and landing format, that is, it can take off this way and land back down this way. And the fixed wing part of the UAV allows for the UAV to be able to fly very long distances in a very efficient manner using the power of aerodynamics, because the wings shall be using the cross section of an airfoil, and the airfoil using the lift equation of half rho a v square cl shall allow the aircraft to fly in a very efficient manner and for long distances. Due to this optimal combination, as we have written here, we have selected this hybrid VTOL UAV. As you can see here, this is a representative diagram of what it may look like. Then we have the autonomous precision landing methods. And these precision landing methods are the ones which will allow for our UAV to autonomously land onto the docking system. And in order to understand what precision landing methods we have used, you can check out our QR code right here. We have an entire table which shows which are the methods that we've used. We checked out 9 different methods, and we have finally chosen the method of using Aruco markers and IR sensors in order to allow our UAV to land accurately onto the moving platform. Aruco markers basically allow for a computer vision system that we have coded to be able to determine the distance of the landing platform in all 3 axes, the X, Y, and Z axes from the camera. Through this, we can give minor and very precise adjustments to the UAV in order to allow it to land properly. And the IR sensors and the IR blasters will be added for extra accuracy, and mainly to allow for the system to also work in the dark, because the Aruco markers will not be visible to the camera in dark conditions. Then finally, we have the UAV docking system and the arresting mechanisms. So the arresting mechanisms are the ones which allow for the UAV to be held in place after it has landed, and these are the ones that are available. They're divided into their active, passive, and combined systems. We have performed a detailed comparative analysis of all of them, which can be checked out from the QR code available in the poster right here. And once we decided what we wish to do with all of these systems, we were able to finalize what our overall execution of the system will be. First, the UAV shall approach the target area. The Aruco markers and the IR sensors will be detected. A precise landing will be carried out. The UAV reaches the arresting area, that is, it will be able to slide to the center of the cones that we have. Once that is done, stabilization will occur. Precision landing will occur, then we shall perform touchdown and stabilization. Then the UAV will be able to slide down to the center of the conical arresting mechanism that we have. Then the arresting mechanism will move to the side using a stepper motor, which will basically hold the UAV in place. Then the electric clamps that we have added shall swing and arrest the UAV. Then the battery swapping will take place, and then the UAV will be able to take off again. Now these are basically the results and the prototypes that we have built. As can be seen here, we have built and we have basically constructed an aerostat and fill it up with hydrogen gas. Now a few additional photos for the aerostat can be shown right here. As you can see in this photo, when I zoom in, you have certain propellers which allow the aerostat to basically orient itself in air while it is floating. And there is also a joined propeller for vertical direction thrust. Then apart from the aerostat, we have our resting and docking mechanism. These four are our docking cones. These are the cones in which the UAV legs shall be placed when they land. And as you can see from this image right here, these cones are actually conical in shape, as the name says, and this allows for there to be a certain error. So even though the UAV may land within a certain error margin, that is these white circles, they will be able to slide back into the center in order to ensure precision. And finally, we can see right here that there are a certain horizontal stays here. These horizontal stays can be grabbed onto using our arresting mechanism, and this arresting mechanism using the stepper motor shall pull the feet apart, and this will be able to hold the UAV in place in highly windy conditions. And we can see that through this video right here of the docking mechanism. So the UAV lands. We were not able to simulate the landing itself of the UAV because this was an indoor environment. But once it does, these stepper motors, as you can see to the sides, they will be activated and they will pull the UAV to the end. They will pull the legs to the side, and this will allow for the UAV to be held in place in extremely windy conditions. Moving on, we have the Aruco markers themselves. This is an example of our Aruco markers that we have used. And as you can see, the three axes, the X, Y, and Z axes can be spotted. And here, the Aruco marker is being detected by the computer vision software that we have used. Apart from this, my project also consists of a simulation in the Gazebo software, which can be seen right here. As you can see, there is a VTOL hybrid UAV that is autonomously navigating to the platform, and it detects the Aruco marker, and using that, it is able to perform a very precise landing onto the platform. Of course, there is a certain margin of error, but that is why our docking and arresting mechanism is able to compensate for that. So as you can see, corrections are being made, and yes, it is visible. It is able to correct itself and move towards the Aruco marker. And once it does, it is able to perform a perfect landing. So these were some of the photos and videos that we wanted to show. In conclusion, we have been able to make an entire system of all of these parts. We have not been able to perform a test of the joint system, but we have been able to perform a test of all of these individual parts, as you can see. Here are some of our references. And finally, here is my acknowledgement. This project was made in conjunction with the LTA Systems Lab and Aerospace Engineering Department of IIT Bombay under Professor Rajkumar S. Pant. I thank him for his leadership and for the opportunity that he has provided me with. Unfortunately, this poster and further information cannot be provided to the public or for display, as this is purely the property of Project Hurkara and I am not allowed to showcase further. Thank you.